In this video, I will write a proof of the absolute convergence test for series. I already wrote the statement in the previous video, and I explained how to use it and why it's useful. This time I want to know why the theorem is true. As a reminder, here's the statement again. I am looking at a series. If the same series with absolute values, making all the terms positive, is convergent, then the original series must be convergent as well. Before doing anything else, I will introduce a new piece of notation. Given a series, I will write pt to represent the positive terms and nt to represent the negative terms. I'll acknowledge that this notation is a bit lazy. To make sense of it, I need to assume that we are talking about one single series at a time and that we have agreed in advance of which series we are talking about. But for the purpose of this video, it will be enough, and it is simple, so I'm going to use it anyway. Let's look at it with an example. Let's say we are studying the alternating harmonic series, 1 minus a half plus a third minus a quarter, and so on. Then, when I write sum of pt, I mean 1 plus a third plus a fifth plus a seventh, and so on. I am keeping only the positive terms in the same positions they were, in the same order, and I have removed the rest. Basically, I'm replacing the negative terms with zeros. And similarly, when I write sum of nt, I mean minus a half, minus a quarter, minus a sixth, and so on, just the negative terms. Okay, now that I have this notation, I want to ask a question that will be the key to the proof. When is it okay to rewrite a series as first adding all the positive terms and then adding all the negative terms? That's a way to reorder the terms. Is it okay? It is certainly okay for finite sums. Finite sums are commutative and associative. If I am adding finitely many numbers, I can choose to first add the positive one and then add the negative ones. But a series is an infinite sum. An infinite sum can be written as a limit of finite sums. So what happens when I take the limit of both sides? On the left, I have the very definition of the series an. And on the right, I have a limit of a sum, which I can rewrite as a sum of two limits. And look at that. Those two limits are, by definition, the series of the positive terms only plus the series of the negative terms only. It looks like I have proven what I was looking for, but there is a big gap in the argument. Can you spot the error? In order to split the limit of a sum as a sum of two limits, I need to use a limit law. As you know, this requires assuming in advance that each one of the two individual limits exists separately. In this case, this means I need to require in advance that the series of only positive terms be convergent and that the series of only negative terms be convergent. With that assumption, I can draw the conclusion I was looking for, but without it, I can say nothing about the original series. The original series may still be convergent or not, I cannot tell. Okay then, so the key observation I was aiming for is this. If the series of positive terms and the series of negative terms are both convergent, then the original series can be written as the sum of the two. Great, this is the best case. The worst case is the opposite, when the sum of the positive terms is infinity and the sum of the negative terms is minus infinity. Then the original series may be anything. It may end up being divergent or convergent. It can still be convergent if I am adding the positive and negative terms in a very specific balanced order in which most of the terms cancel out or something. That is what happens in conditionally convergent series, and is the reason why conditionally convergent series are not commutative. But that's a tangent. If this intrigues you, I invite you to watch the next video where I will elaborate on it. For now, let's go back to the actual goal of the video. I wanted to prove the absolute convergence test. Now that we have made the previous observation, the proof will be very short. Here it is. Let's assume that the series of the absolute values of an is convergent. Notice that the sum of the absolute values of the positive terms and the sum of the absolute values of the negative terms are both bounded by the sum of all the absolute values. Therefore, by the basic comparison test, they are both also convergent. That means that the sum of the positive terms and the sum of the negative terms are themselves convergent. because they are equal to plus in the first case and minus in the second case, the previous two sums. Then, by the key observation we made earlier, the original series is equal to the sum of these two, and it is convergent. That is what I wanted to prove. We're done.